Great. So now that we've done one element, two elements, now we can go and say, okay, let's see what it takes to write a finite element program where we have lots and lots and lots of elements. And let's look at that in this 1D example. Once we're done with this, we almost going to get to a point where we're going to close on the one-dimensional finite elements, and then we can extend towards two-dimensional finite elements and really extend what we've learned beyond. So that is really exciting what's lying ahead for us, so that we can then really make sure that we can reflect on what we've done in 1D, think critically how to extend it to 2D and 3D without really having to go through all the details of the mathematics, but that we just can really reason about it quite sensibly. But before we do that, let's look at what this 1D finite element holds for us. Okay. So, well, the reality is if you want to write a systematic finite element program, we first really like to go and say, let's try to write small functions that takes this big problem that is a finite element program and breaks it into smaller chunks. And that is really how any of these projects that you would tackle that's maybe a little bit longer would work. That's what you've also learned in NPR 2 and 3. If you have a complex problem, break it down into a lot of smaller problems. The smaller problems are solvable, and then you pack them together like a puzzle to create a complex picture or solve a complex problem. Okay, so let's consider the case where we have a bar that's clamped at x0, force 1,000 newtons, and the right edge at x equals to 1. Okay, area varies linearly, so we have a thick. Oh, sorry, there's a typo here. There should be +1. The area is essentially thin at the one side, it gets thicker towards the other side with the x equals 1 side. Then we have a Young's modulus of 202 gigapascal. Okay, so that is essentially first step. So what we could do is to say, let's write down an expression for our constitutive of our Young's modulus. So that's essentially this value that we've just coded in here in gigapascal, but we just converted it now to Pascal as a function of psi. Okay. So although this is a constant, if I plug in any psi, I will get out a value of 210. Obviously, this could also become then later on a function of psi. So we can have very little materials as well. We can check whether shape functions. We can write small little utility functions for them, say n1 to n3. These are shape functions that we have. We can construct the derivatives of the shape functions. That's essentially what we do here. So now we're coding the shape function, the derivatives. So this is just the numerical version of going about this, all using NumPy, essentially, a sort of numerical approach. No SymPy is being imported yet. And this is how most of the typical finite element approaches would work. Okay. Construct the function that returns the mapping between x and psi. That's essentially our isoparametric formulation that we have here. So give it the coordinates. Yeah, so the coordinates for in x, and then at psi, and then out will pop the x value for that given psi. So that's essentially what we have there. Construct the function that returns the local displacement field as a function of psi, local nodal displacements. Okay, so this is again Q's, and they are known. Specify psi, give me the nodal values, and I would be able to return for you u at that specific value of psi. Okay, setting up the dn psi matrix. In this case, essentially in this case, it's just a row vector. Okay, let's note that there's a vector inside another vector, so it's a matrix. In this case, a 1/3 matrix. The x d psi is my relationship between x and psi. I have changes in those two worlds. My b vector is telling me essentially what's going on in terms of the derivative of this with respect to a spatial variable x. This is what this is. Area we can define as part of the problem, the function of psi. So everything that we define here is really a function of psi. And this is done, as we know, for the integration, to make integration easier. Okay, now we can go about and say, fantastic, let's get the integrand. Yeah, so here I compute the integrand for that matrix, for that element. This quadratic element, there is that, and there's my term that comes out. So this k term is just the integrand that we're computing. And then we can say, okay, now we can go about integrating this. So here are some examples of check here, what is this quickly? Oh yeah, it's just a lot of zeros in here. A lot of these values just so that we can stack them into rows. So for a 2x2 rule, we'll use the first two values here, and we have the associated weights. So if we have higher order rule, 3-point rule, then that's what we'll have, and here's the associated weights. So here's we're just stacking a matrix with all the rows of all the values in there. So that's why you see a lot of these zeros. So just you want to access them for the 2-point rule. You want to access these two values. It's just one way of doing it. Alternatively, one could have stored this into a dictionary, and then just stored whatever values were required, and have to have padded it with a lot of zeros. Okay, so that's something simple there. Now we can go and say, let's compute the local stiffness matrix. Supply for that the local nodal coordinates. So that's important to supply that, and then we can start going and do Gauss quadrature integration. Okay, so typically you might even want to specify the number of Gauss points, and then use that. Okay, so that's depending on how you want to approach this. As this is something that you could also specify here at the moment. Gauss quadrature points is hard coded. Okay.